Okay, so in the previous video we introduced the idea of a transition matrix as a way of describing how if we have a system where there are two possible states, we could be at a warehouse A or warehouse B, we could be on or off, we could agree or disagree, whatever it might be. And then we have information about how those states change or transition, okay? This proportion of those things that were at A go to B, and this proportion that were at A stay at A, whatever it might be. We can create something called a transition matrix. What we want to now look at in this video is how we can utilize that transition matrix in dealing with these sorts of situations. Okay, so let's return to the example that we looked at in the previous video, which was delivery trucks transferring goods between two warehouses, A and B. And we had that information in a table and also in a transition diagram, which are both pictured here. Okay. So what we want to then think about is, okay, well, we now know how the trucks move between the two warehouses on a daily basis. So if we knew that there was 20 trucks at warehouse A and 30 trucks at warehouse B on Monday morning, we could then use the above information to calculate the number of trucks at each depot on Monday night or Tuesday morning, so at the end of Monday or start of Tuesday. So, as I said, if we know that there are 20 trucks at warehouse A, and we know that 70% of the trucks at warehouse A end up at warehouse A, then we do 70% times 20, which gives us 14, and we know that 14 of those 20 trucks will end up at warehouse A at the end of Monday, and we know that the remaining 30%, which is 6 trucks, will move from warehouse A to warehouse B. Okay. If there were 30 trucks at warehouse B on Monday morning, then we know that 60% of those trucks stay at warehouse B, so 60% of 30, 0.6 times 30 is 18 trucks, they stay at warehouse B, and the remaining 40%, which is 12 trucks, they go from warehouse B to warehouse A. And so what we find in terms of the trucks that will end up at warehouse A, there's the 14 trucks that started at warehouse A and will stay at warehouse A, and the 12 trucks that started at warehouse B and will end up at warehouse B. So in total, 26 trucks end up at warehouse A. So in the morning there was only 20, by the end of Monday / Tuesday morning there will now be 26 trucks at warehouse A. Okay. We also know that 6 trucks move from warehouse A to warehouse B, and 18 trucks started at warehouse B and stay at warehouse B, and so there's 24 trucks in total that will end up at warehouse B after one day. Okay. So earlier we also converted the transition diagram or table into a transition matrix, which was this. Remembering the important thing about a transition matrix is that the columns must add up to 1. Okay. We can also write the information about the initial distribution of trucks. So the Monday, the fact that we know that there were 20 trucks at warehouse A and 30 trucks at warehouse B on Monday morning. We can write that information in also in a matrix. Okay, we call this the initial state matrix. So on Monday morning, this is what's happening. So in our transition matrix, this is warehouse A and B. Okay. The top row is A and the bottom row is B. So in your state matrix, it must be consistent with that. So the top row must be the initial state of A and the bottom row must be the initial state of B. Okay, so top row here is about trucks that end up at A. Okay, top row here needs to be trucks that are at A. Bottom row is trucks that end up at B. Bottom row must be about B. Okay, so it's important that you're consistent about that. So we could then calculate, having now established the initial state. Okay, we know how things transition, we know how to get from one state to the next state, and we know what the initial state is. From here we can now start to create the chain. Okay, well what's the second state? The initial state we call state 0. So what's the first state? Which would in this case, so state 0 being Monday morning. What's Tuesday morning? Which would be state 1. Okay, what's Wednesday morning? Which would be state 2. What's Friday morning? Which would be state 4. Okay. So once we've got it's a bit like, and I'll mention the word recurrence relation in a minute, it's just like back in financial maths when we start with, a recurrence relation. What's the initial value and how do we get from one value to the next? That's exactly what's happening here. We're going to talk in those terms in a little bit. So S0 is our initial state, T is our transition matrix. We could then calculate the next state, which is the distribution of the trucks on Tuesday, and it would be called state 1 by applying the transition to the initial state. Okay, so if we do transition matrix times S0. Now we have to do it in that order just to get the matrix multiplication to work. This is 2 by 2, this is 2 by 1. We can't do S0 times 0, S0 times T, that's not defined. So we do the transition, multiply that by the initial state, okay? And that will give us the first state, the next, which is just the next state after the initial state. So when we do that, we can see we've got the CAS screenshot here, which has done that multiplication for us, and we find that we get 26 and 24. So we see that on Tuesday morning, there'll be 26 trucks at warehouse A, or Monday night, and 24 trucks at warehouse B. Okay, so then if we wanted to take it another step, we wanted to know, well, what happens on Wednesday morning? So this was now Tuesday morning, so then we can apply the transition again to what's happening on Tuesday in order to work out what happens on Wednesday. So again, do the matrix multiplication, it's happening here in the second row of my CAS, and we find that there'll be 27.8 trucks at A and 22.2 trucks at B. Now, because we're talking about trucks, having decimal values makes no sense, so for practical reasons we would need to round these answers to the nearest whole number, which would mean we would say that on Wednesday morning there is 28 trucks at warehouse A and 22 trucks at warehouse B. So as I said, what we're using here is a recurrence relation, how to transition from each state to the next. So to get from the nth state to the n plus 1th state, so to get from one state to the next state, we need to multiply by the transition matrix. Okay? So that means if Monday morning is state 0, Tuesday morning is state 1, and we get from state 0 to state 1 by multiplying by the transition matrix. Okay? If we then want to get to Wednesday, Wednesday morning is state 2. Okay? So to get from Tuesday to Wednesday, we're going to take Tuesday's state and multiply it by the transition matrix. Okay? But that's the same as, well, Tuesday's state, S1, that was S0, Monday's state, times the transition matrix. So actually, if we think about what we've done to get to S2, all we've done is multiply by the transition and again multiply by the transition. So we've actually multiplied the initial state by the transition matrix twice, so by t squared. Okay. Again, if we wanted to get from Monday to Thursday, times by the transition, times by the transition, times by the transition again. To get from Monday to Thursday is 3 transitions. So we're going to take Monday's state, S0, and multiply it by the transition matrix 3 times. We could also just take Wednesdays and multiply it by the transition matrix once. But the point is that we want to not have to, if I know about April, if I know about January, I don't want to have to work out, say, a different situation working on a monthly basis. I don't want to have to work out February, March, April, May, June, July, August, September, October, all just to get to November. I want to know a way that I can get straight from January to November. So that's what we're looking at here. It's about working out how many transitions are happening to get from this state to this state. So if I want to go from state 0 to state 5, okay, to get from 0 to 5 is 1, 2, 3, 4, 5 transitions. So I'm multiplying by the transition matrix 5 times. Okay, so if we want to do that, we can get our CAS to do that straight away to work out the 5th state, which in this case would correspond to Saturday morning. Okay, we take our initial state, which was 20 and 30, 20 trucks at warehouse A, 30 trucks at warehouse B, and multiply it by our transition matrix to a power of 5, and we see that we get this. So again, we would need to round because we're talking about trucks. So we can see that on Saturday morning there'll be 29 trucks at warehouse A and 21 trucks at warehouse B. So generally speaking, the state matrix after n transitions can be calculated as follows. So if we know S0, we multiply by the transition matrix n times and it gets us to Sn. Now, I want you to be cautious about this formula. I don't want you to think about formula here. It's not helpful, okay? So let's say, for example, as we just did, if I know about the 0th state and I want to get to the 5th state, how many transitions are needed to get from 0 to 5? To get from 0 to 5, I count 1, 2, 3, 4, 5. I need 5 transitions, okay? Let's say you didn't know about S0. Let's say you knew about S1 and you want to get to S5, okay? How many transitions do you need to get from the 1st state to the 5th state? To get from 1 to 5, I count from 1, 2, 3, 4, 5. I need 4 transitions to get from 1 to 5. Let's say we know about S3 3, the third day, and we want to get to the 10th day or month or week or whatever the problem's about. How many transitions are needed to get from 3 to 10? Getting to 4 will be 1 transition. Getting to 5 will be 2 transitions. 6, 7, 8, 9, 10. Okay, it's 7 transitions that are required to get from stage 3 to stage 10. So I don't want you to get bogged down in formula. I want you to think practically. If I'm here and I want to get here, how many transitions do I need? We'll talk more about this in some more complicated examples later on, but let's say we are at we know about day 10 and we want to get to day 3. Okay, how do we get from 10 to 3? We have to go, it's 7 transitions, but it's 7 transitions backwards. Okay, so actually if you think about, we know that t to the power of 7 times s3 would give us s to the 10. Actually, to get from stage 10 to stage 3, you would go backwards by 7 transitions. But that's quite complicated. We'll talk about that in some heartier examples a little bit later on. Okay, but again, I don't want you to get confused by formula. I want you to think really practically about what's happening in the problem. Okay, let's work our way through 2 examples and then we'll talk about adding in the steady state. So a survey shows that 75% of the time, customers will continue to purchase their groceries from store A if they purchased their groceries from store A in the previous month, while 25% of the time, consumers will change to purchasing their groceries from store B if they purchased their groceries from store A in the previous month. Similarly, the records show that 80% of the time, consumers will continue to purchase their groceries from store B if they purchased their groceries from store B in the previous month. Set up a transition matrix to represent this information. Okay, so our transition matrix, and we're going to be, remember it's always from store A and B and to store A and B in our matrix. Okay, so 75% of the time, customers will continue to purchase from A if they previously purchased from A. That's from A to A is still 75%, so 0.75 goes there. The next sentence, it doesn't need to be given to us because we automatically know the column has to add up to 1, and so we know that there must be 0.25 here. But it does say that in the question. 25% of the time, customers change to purchasing their groceries from store B if they purchased from store A in the previous month. So from store A, they move to store B 25% of the time. Okay, so that's what we've got in our matrix. Similarly, records show that 80% of the time, consumers will continue to purchase groceries from store B if they purchased from store B previously. Okay, so 80% of the time they'll stay with store B. If they were from store B in the previous month, they will still be with store B in the next month. And so that means 20% will go from store B to store A. Okay. All right, if 200 customers started at store A and 400 customers started at store B, find, correct to the nearest whole number, the number of customers shopping at each store at the end of 1 month. Okay, so what we've got here in this sentence is S0. At the beginning, we have 200 customers at store A and 400 customers at store B. Okay, we want to know the number of customers shopping at each store at the end of 1 month. So stage 1, okay, will be stage 0, so our initial state, multiplied by our transition matrix. Okay, so if I put that information in my CAS, let's get my 2 by 2 matrix, which is 0.75, 0.2, 0.25, and 0.8. And we want to multiply that by 200, 400. Okay, and so we get 230, 370. It's really important that you answer the question in these problems. So you need to interpret out of the matrix which number represents which quantity. Okay, so you must make sure you answer the question. So find the number of customers shopping at each store at the end of 1 month. Okay, so 230 customers at A, let's say store A, and 370 customers at store B after 1 month. Find the number of customers shopping at each store at the end of 3 months. So we want S3. we know about S0. To get from S0 to S3 is 3 transitions. So I'm just going to, in my CAS, I'm going to scroll up and get this calculation here, press enter to copy that down, and this time instead of just doing 1 transition, I'm going to do 3 transitions. And we find now their number of customers, so we'll round to the nearest whole number. So it doesn't need to say that here because we're giving a number of people. Okay, can't have 255.6 people. So 255.57 rounds to 256 people, and 344 will round down to 344. Okay, so therefore 256 customers at store A and 344 customers at store B. What percentage, correct to the nearest percent, of customers are purchasing their groceries at A and B at the end of 6 months if 50% of the customers started at A? Okay, so you can do this in a couple of ways. What you can do is say, okay, there were 600 customers. If it was 50-50 at the start, we could now make S0 300, 300. Oops, 300, 300. And then you could work out how many customers there were. Sorry, let me just move that. Then you could work out how many customers there were after 6 months. So S6 would be T to the 6 times S0. Okay. I'll do this. Don't write this down just yet, and you can choose which answer you prefer to write down. So if instead we said, okay, we're going to do 6 transitions, and the initial state wasn't 200, 400, it was 50-50 at each store, so that means it's 300, 300. Okay, so what you could then do is work out, okay, well that's 260, rounding, 268 customers there and 332 customers there at A and B. And what percentage of customers are purchasing their groceries at A and B at the end of 6 months if 50% of the customers started at A? So then we could work these out as percentages, okay? So the percentage at A is going to be 268 people out of the original 300 that were at A, and times by 100 to make a percent. 268 divided by 300 times by 100. Okay, do that again and press Control Enter. Okay, so that's 89% to the nearest percent, which means we could do the separate calculation, or you'd automatically then know it'll be, oh no, sorry, it won't. We'll do the separate calculation. So 332 customers out of the original 300, and now at store B. Sorry, it's not compared to the original. My apologies. That's not the right percentage calculation. So we want to know there's 600 customers in total. Sorry. So 200, not 300. So 268 customers are at A out of the 600 customers in total, converting to a percentage. So 268 divided by the 600 customers times by 100 to make a percent. So we're finding that 40 to the nearest percent, 5% of customers shop at store A, and then we can automatically infer from that that 55% are shopping at store B. So you can do it that way, but actually another way you can use your initial state matrix is you don't need to have numbers of customers in here, okay? Instead, you could have proportions of customers. So we could say that our initial state is 50-50. 50% are at A and 50% are at B. And so then, when you do your matrix calculation, instead of it being T to the power of 6 times 300, 300, your initial state is 0.5, 0.5. 50% are at A, 50% are at B. And what this means is the numbers we'll get will be the percentages at each store. And immediately here we get 0.45 and 0.55. So if we want in the end what we want in the end is a percentage answer of what percentage shop at each store, then we can write our initial state as what percentage initially shop at each store. Okay, so therefore we have 45% at store A and 55% at store B. So much easier to just put percentages in your initial state matrix if what you want in the end is percentages. But it's possible to get there by thinking about 300 people shopping at each store initially and then calculating your percentages at the end. Okay, second example. If a train is late on one day, there is a 15% probability that the same train will be late the next day. If the train is on time one day, there's a 40% chance that it will be late the next day. If in a given week a train arrives on time on Monday, calculate Okay, let's form our transition matrix first. So I'm just going to do that off to the side over here. Should leave myself some room. So we're going to have a train that is, okay, that's my transition matrix. The train is either on time or late, and then the next day it can either be on time or late. So remembering this is going to be, the day one and then day two, okay? So we go in this direction when working from our matrices. So if the train was late on one day, so if it's originally late, there's a 15% chance it will be late again the next day. Okay, so that's going to be that number down there, 0.15. Okay. If the train is on time one day, there's a 40% chance it will be late the next day. So if it is on time on the first day, there's a 40% chance it will be late the next day. Okay, so remember, columns in our transition matrix have to add up to 1, so this has to be 0.6 and this has to be 0.85. So there's our transition matrix. If in a given week, if a train is late on one day, okay, so we want to find if in a given week a train arrives on time on Monday. So on time on Monday is giving us our initial state. So we know that S0, which is Monday, it's definitely on time on Monday. So because we're dealing in probabilities here, okay, the probability of the train being on time on Monday is certain. So definitely on time on Monday, definitely not late on Monday. So S0 is 10. Okay, so we want to find, so 1 being a certain probability and 0 being a no chance probability. So we know it was definitely on time on Monday. We want to know the probability that the train will be on time on Wednesday. Okay, so S0 is Monday, okay? So that means that Wednesday, that would mean S1 is Tuesday and S2 is Wednesday, okay? Doesn't really matter. We could call this S1 and then it would be 1 and 3. It doesn't really matter what we call them, okay? The point is that it's how many transitions does it take to get from Monday to Wednesday. So if we call Monday S0, Wednesday is S2, it's 2 transitions. If we call Monday S1, Wednesday is S3, it's still 2 transitions. So it's still the same calculation, okay? So we're doing 0.6, 0.4, 0.85, 0.15, multiplying by 10, the transition matrix squared, and then multiplying that by 10 to get what's happening, what are the probabilities of the train being late and on time on Wednesday. Okay, so let's put that in. Let's get our 2 by 2 transition matrix, 0.6, 0.85, 0.4 and 0.15, and we're squaring that and we're multiplying that by 10. Okay, so we get 0.7 and 0.3. Now this is where we then need to make sure that we answer the question. Find the probability that the train will be on time on Wednesday. So we're not interested in both of these numbers in answering the question. The top row in our matrix is about on time. So therefore 70% chance the train will be on time on Wednesday. Okay. Find the probability the train will be late on Friday. Give your answer as a percentage to correct to 1 decimal place. Okay, so Friday, so if S0 is Monday, Friday is 4 days away, it's S4. It's 4 transitions from Monday to Friday. Count it out on your fingers if you need to. Tuesday, Wednesday, Thursday, Friday. 4 transitions, okay? So we're doing our transition matrix to the power of 4, and we're multiplying that by our initial state, which said the train was on time on Monday, and we get our CAS to do that. I can just manipulate my previous calculation, so scrolling up and pressing enter, changing that power of 2 this time to a power of 4. And we want percentage to 1 decimal place, so therefore I'm going to need 3 decimal places here, so that's 0.681 and 0.319. Okay, find the probability the train will be late on Friday. So that is this number here, okay? So therefore, 31.9% chance the train will be late on Friday. Okay? Alright, example 3. A railway company owns 250 goods wagons which are used to transport goods between point A and point B. At the end of each week, the company finds that 10% of the wagons that started the week at point A ended up at point B, and 8% of the wagons that started the week at point B ended the week at point A. Write down a transition matrix. Okay, so to A and B and from A and B. Okay, so remember from to, always going this way in a transition matrix. At the end of the week, company finds that 10% of the wagons that started at A ended up at B. So started at A, ended up at B is that. So this is 10% or 0.1 here, which means this must be 0.9 because columns add to 1. 8% of the wagons that started at point B ended up at point A. So from B to A is 8%, 0.08. Okay, which means that 92%, 0.92%, started at B and stayed at B. So there's our transition matrix. At the end of week 4, there are 100 wagons at point A and 150 wagons at point B. Okay, week 4, let's therefore call it state 4. We could call it state 0, but that's going to make everything else a bit more complicated. So let's say we know what's happening at week 4. State 4, we've got 100 wagons at A and 150 wagons at B. Okay, so we want to know the number of wagons in each location at the end of week 7. So we want state 7. We know about state 4. So the question is, how many transitions to get from state 4 to state 7? Count on your fingers if you need. 5, 6, 7. So 3 transitions are going to be needed to get from state 4 to state 7. Okay, so our calculation is our transition matrix, 0.9, 0.1, 0.08, 0.92 to the power of 3 times 100 and 150. Okay, let's do that. 2 by 2 matrix, 0.9, 0.08, 0.1 and 0.92. Now we want power of 3 and we're multiplying that by 100 and, 150. Okay, so that is, and again we're talking about number of wagons, so they need to be whole numbers. That is 105 to the nearest whole number and 145 to the nearest whole number. They should still add up to the same total. So if you started with 250 wagons, you should still have 250 wagons when you do your rounding. If you've got 3 states, sometimes that rounding ends up slightly out, but when you've got 2 states, it should always round, so you've still got the same number. Okay, so again, we want to make sure we've answered the question, which was to calculate the number of wagons in each location at the end of week 7. Okay, so therefore we have 105 wagons at A and 145 wagons at B. Calculate the number of wagons in each location at the end of week 3. Okay, so we want to know, I talked briefly about this earlier, we want to know about stage 3, given that we know about stage 4. Okay, so that's a more complicated question to think about that. So instead, let's think about, we know if we want to get to stage 4, we would do 1 transition times stage 3. Okay, so that means we know this. So we know that this is 100 and 150. And we know the transition matrix. And we're going to need to solve for S3. So let me just not write that for a second. So if we want to actually solve for this, again, it's about solving a matrix equation. So we would need to use the inverse of t here to cancel that out from there, which means we would need to use the inverse of t over here. And so what we actually find is that stage 3 is the inverse of t times stage 4. But actually, it means that we can think about this in the same way that we think usually about how many transitions are there to get from stage 4 to stage 3. There's -1 transitions, and that becomes my power. okay? And we can actually extend that out if we wanted to go further back in time. But it comes from this using our inverse matrix to solve that equation, okay? So in this case, we're going to take our transition matrix, raise it to a power of -1, and times it by stage 4, which was 100 and 150. And so what we find is stage 3, again, nearest whole number is 98 and 152. Okay, number of wagons in each location, so therefore in week 3 we have 98 wagons at A and 152 wagons at B. Calculate the number of wagons in each location at the end of week 1. So again, we want to think relative to week 4. Alright, and let's think about the logic we used here. So we know about stage 4, that's the initial state we've been given. We want to get to stage 1, okay? How many transitions is that? Well, that's going back by 3 transitions. What we will find is if we do t to the power of -3, which is essentially multiplying by the inverse matrix 3 times, we're going to get the matrix that we want. So again, let's just edit our previous calculation in our CAS. So transition to the power of -3 times 100, 150, and we find that week 1 was, again, to the nearest whole number, 91 and 159. So therefore, 91 wagons at A and 159 wagons at B. Okay, next thing we want to talk about, I warned you this would be a long video. There's quite a natural break there if you want to sort of pause, go away and have a start on the exercise. The reason, however, that I include these together is because the exercise, most of the questions include the steady state right from early on in the exercise, so it's hard to break up the exercise of questions at this point. So I'm going to keep going and talk about the steady state solution. So when we have a 2-state Markov chain, so that is where our transition matrix is 2 by 2, because at every state we can be in one of two, at every moment we can be in one of 2 states. So whether that's warehouse A and warehouse B, or on or off, or on time or late, whatever it might be, there's only 2 states that we could be in. So that's a 2-state Markov chain. When we have a 2-state Markov chain, a steady state is always reached. Okay, and we'll talk about what the steady state is in a bit. So what that means is that while the numbers in each state might vary somewhat initially, they eventually reach an equilibrium point. So if you continue with your trucks moving between your 2 warehouses, at some point the numbers are going to reach a sort of equilibrium point where even if 20% of the trucks go from B to A and 40% go from A to B, you'll get the numbers at A and B such that 20% of the trucks at B is the same number of trucks as 40% of the trucks at A. And so what's happening each day is that the same number of trucks end up moving, and that means that the number of trucks at each warehouse remain the same every time from then on. And therefore we've reached what we call the steady state. So if, for example, we go back to our trucks moving between warehouse A and B, you'll remember that our initial state, which was Monday morning, our initial state, which was Monday morning, was this. There were 20 trucks at warehouse A and 30 trucks at warehouse B. We then apply our transition matrix once to work out what's happening on Tuesday, and we find that Tuesday, after 1 transition, we have 26 trucks at warehouse A and 24 trucks at warehouse B. Then on Wednesday, we apply the transition again, and we now have 28 trucks at warehouse A and 22 trucks at warehouse B. Thursday, we apply the transition once again, so now it's t cubed times the initial state, and we've got 28 trucks at warehouse B, so I'm having to round, so they're not exactly the same numbers if they're not rounded, but in terms of whole numbers, we still have 28 trucks and 22 trucks. Stage 4, okay, so again we multiply by the transition matrix, we're now seeing 29 trucks at warehouse A and 21 trucks at warehouse B. Okay. Stage 5, still 29 and 21. Stage 6, still 29 and 21. You can see if we actually look at the unrounded decimal values, okay, so they're rounding to 29 and 21, but they're not exactly 29 and 21. But what you'll see is they are getting more the same. So this decimal here is not the same as this decimal here, so there's still a bit of change happen, but to the nearest whole number they're the same. Okay. However, once we get down to here, this decimal to 4 decimal places, not quite the same, but it's the same to 2 decimal places. Okay. This is now the same to 3 decimal places. Okay. So ultimately, in practical terms, though, we've reached a steady state where every day we've still got 29 trucks at warehouse A and 29 trucks at warehouse B. 21 trucks at warehouse B. And that's because if we have a look at the numbers in the transition matrix, 40%, okay, so 40% of the trucks go from warehouse B to warehouse A, and 30% go from warehouse A to warehouse B. Okay, so if there were 29 trucks at warehouse A and 30% of them go to B, okay, if I do 0.3 times 29, times 29, that's 9 trucks. Okay, 9 trucks going from A to B. 21 trucks at B, I know 40% of them go to A, so 40% of 21 is also is 8 trucks. Sorry, so we're not quite there yet. But what you find here is that you've reached the equilibrium where essentially the same number of trucks are moving from one state to the next state. Okay. So ultimately we see that if we were to continue on here forever, it would from this point onwards still be every day 29 trucks ending up at A and 21 ending up at B. And we've ended up at a sort of equilibrium point, and we call that the steady state solution. So the steady state solution would be 29 trucks at A and 21 trucks at B. Sometimes we also talk about the long run solution. In the long run, we would end up with 29 trucks at A and 21 trucks at B. You'll never need to work out when that actually happens because it comes down to a question of rounding, but the idea is over the long term, what will happen? So essentially the steady state solution can be obtained by applying a large number of transitions to the initial state. What we actually saw here is that 10 transitions was more than enough. What I would usually say is I would normally apply 50 transitions. In terms of what we write, in terms of the steady state solution, we're actually finding S infinity. Okay, we're finding what happens as time heads on forever. Okay, but it's not practical to raise transition. It's not practical to raise the transition matrix to the power of infinity. So in practice, we would raise it to a power of 50, and then what I would also do is I would raise it to a power of 51 and check that I've actually got the same solution, so that I know that I've reached the steady state. Okay, let's have a look at how that works in practice through to a couple of examples. An insurance company needs to measure its risk if it is to underwrite a policy for a major outdoor festival. The company used the following information about the region. Long-run data gathered about the region's weather suggests that there is a 75% chance that if today is dry, the next day will also be dry. Conversely, if today is wet, there is a 72% chance that the next day will also be wet. This information is given in the table below. Okay, so today to tomorrow, so it's set up in the right way for the transition matrix. So this is essentially our transition matrix. Okay, columns add to 1. Okay, probability if today is wet, tomorrow is wet is 0.72, etc. So there's our transition matrix. If the weather is initially dry, S0, so we've got it's dry and wet. Dry is the top row and wet is the bottom row. So it's definitely dry. So one probability of 1 that it's dry, probability of 0 that it's wet. Okay. Find the long-term probability of rain. Okay, so what we want to know is the long-term probability. So technically what we want to work out is S infinity, the steady state solution, okay, which would be our transition matrix to a very large power multiplied by our initial state, which in this case is going to be 1, 0. So I'm just going to move this over so that I've got a bit more space. So we're saying S0 here is 1, 0. Okay. So in practice in my CAS, obviously I'm not going to put t to the power of infinity, but I'll just put t to the power of 50 in my CAS, but I am still working out the steady state solution, so on the paper I'm going to write infinity. So 0.28, 0.25, and 0.72. I'm going to raise that to a power of 50, and we're going to multiply that by the initial state, which is 1, 0. And just to check that I've actually reached the steady state, I'm also going to see what happens after 51 transitions. And yes, we can see they're the same, and so we've definitely reached, this is definitely the steady state. We want correct to 4 decimal places, so it is 0.5283 and 0.4717. Okay, we also want to know the long-term probability of rain, so we want to select out the number that's actually relevant. So wet is the bottom row, okay, so therefore long-term probability of rain is 0.4717, so just under half. If the weather is initially wet, find the long-term probability of rain. Okay, so initially wet, so that means now, in this question, S0 is 0.1. Definitely not dry, definitely is wet. So, steady state solution. So I'm just going to edit my previous calculation to power of 50, but it's now going to be, 0.1. And I'm just going to check 51. Same. Okay, good. So 4 decimal places, 0.5283, 0.4717. Long-term probability of rain, if it was initially wet, is also the same as what we got in part A. And that's not an accident. Long-term probability of rain is 0.4717. So one of the features of the steady state solution is actually not only have we reached a point where things will remain the same from there on out, it's also independent of the initial state. Okay, so regardless of whether there had been, whether it was wet initially or dry initially, the long-term probability of rain is 0.4717. So actually that means that if you want to work out the long-term probability or what's happening in the long term, you actually don't need an initial state at all. You could just raise your transition matrix to the power of 50, and what you see here is that the top left number is telling you if it was wet on the previous, if it was, if it was dry on the previous day, there's a 52% chance it's dry the next day. If it was wet the previous day, there's still a 52% chance it's dry the next day. So the probability of it being dry the next day, probability of it being dry is 52%. And 47%, or 53, sorry, rounding to 1%, rounding to the nearest percent, and 47% that it's wet. Okay, so you actually don't even need the initial state to work out the long-term probability. Okay, it should be the same regardless of what the initial state is. The company will only insure the festival if the long-term probability of rain is less than 50%, and we've found that through both part A and B, the long-term probability is 47%, and so the insurance company will insure this event. Yes. The long-term probability of rain is 47.17%, which is less than 50%. So the company will insure the event. Insure the event. So for them, the risk of rain is low enough for them to insure it if it's a less than 50% chance of rain. Obviously, they've worked out what those margins are, what those risk levels are, but that's their decision. Okay, example 5, I think this is the last example. Sorry, I know this has been a long video. Yep. So the following information related to a survey conducted in October 2012 on supermarket shopping. 12% of store A customers will shop at store B in the following month. 36% of store A customers will shop at store C in the following month, etc., etc. So what we see here is we now have 3 stores. This is a 3-state transition matrix, okay, or a 3-state Markov chain, sorry. So we'll have a 3x3 transition matrix. So from store A, from store B, from store C, to store A, to store B, to store B, to store C, sorry. So 12% of store A customers will shop at store B in the following month. So if they were store A, they will become store B at a rate of 12%. So 0.12 goes there. 36% of store A customers will shop at store C in the following month. So if they were store A customers, there's a 36% chance they will become store C customers. Okay, so that's 0.36 goes there. Therefore, we can work out what the what percentage stay store A customers by knowing that they have to add up to 1. So if I do 1 minus 0.36 and minus 0.12, that means I've got 0.52 left, so 52% left that stay shopping at store A. Okay, 40% of store B customers will shop at store B in the following month. So from B to B, 40%. 44% of store B customers will shop at store C in the following month. So 44% will go from B to C, and therefore we can work out what percentage are left to shop at store A. So only 16% will go from store B to store A. 14% of store C customers will shop at store A in the following month, so that's 0.14 up here. 7% of store C customers will shop at store B in the following month, so 0.07, and therefore we can work out how many will stick with store C. Seem to be pretty loyal to store C. I'm sorry, did times 0.07 rather than minus. So 0.79 remain with store C. The market share at the time of the survey showed that 1,200 customers shopped at store A, 800 customers shopped at store B, and 1,000 customers shopped at store B. So this is S0. The time of the survey, 1,200 at store A, 800 at store B, and 1,000 at store C. Find the number of customers expected to be shopping at each store in March 2013. Give your answers to the nearest whole number. Okay, so let's go back and be clear about what's happening here. So October 2012, and this is a monthly transition. Okay, so the transitions happen monthly. That's important to note from your information. And S0 is October 2012. Okay. So we want to work out how to get to March of 2013. So again, get your fingers out. October, so one transition to November, December, January, February, March. So March 2013 is 5 months after. Okay, so October 2012 to March 2013 is 5 months. Okay, so we're going to need 5 transitions. So we're going to have, so that means that March 2013 is state 5. Okay, and it's going to be 5 transitions times state 0. I've already got my transition matrix and state 0 clearly written further up here, so I don't actually need to write them in the calculation here. Okay, I can just, as long as they're clearly written somewhere in the question, I can just write t to the power 5 times s0. Alright, let's do the calculation. Transition matrix, we need a 3 by 3. So 0.52, 0.16, 0.14, 0.12, 0.4, sorry, that cursor's in the way there, 0.07, oh sorry, 0.07, 0.36, 0.44, 0.79. Okay, we're going to do that to the power of 5, and then we're going to multiply that by our initial state, which is a 3 by 1 matrix, 1,200, 800, 1,000, 1,000. Okay, and we want nearest whole number because obviously it's number of customers. Sorry, let's change back to the pen. So we've got 694, 369, and 1937 to the nearest whole number. Find the number of customers expected to be shopping at each store in March 2013. So March 2013, store A is 694 customers. Store B is 369 customers, and store C is 1937 customers. Okay, so store C is going very well. They've nearly doubled their clientele in those 5 months, and that's because their clients, their own clients, were very loyal. 80%, nearly 80% of them stayed with store C, and then there were quite a lot of clients from the other stores that were moving from those stores to store C. Obviously, word got out about how good it was. Calculate the long-term share of customers at each store as a percentage, correct to the nearest percent. Okay, so we have to calculate some percentages, and we could do this in 2 ways. We could either convert our initial state to percentages. Okay, so if we work out the total number of people, customers, 1,200 plus 800 plus 1,000. Okay, so it's 3,000 in total. So 1,200 out of 3,000. So that's 40% of the initial customers are at store A, 800 out of 3,000. 26.6 recurring. Now, if that was a whole number, I'd go with this, but that's going to be hard to reflect accurately. So this, I'll probably calculate my percentages at the end, just to be careful. Sorry. And then this will be 33.3 recurring. Okay, so if these were nice whole numbers, I'd probably use the percentages. So these aren't actually equal to each other. But given that we've got, I'm not going to type in the recurring decimals, so I'm going to stick with my S0 as it is and change to percentages later. But if you changed S0 to be in percentages, then you wouldn't need to change after you've calculated the steady state. Actually, or we could do this one other way. I'll have a look at that as well. So let's have a look at, we're calculating the long-term probabilities. So transition matrix to a large power times by our initial state. So let me go back up here and get one of these calculations with this transition matrix here. Okay, let's make it a power of 50 instead of a power of 5. And let's just check that when we do 51, we still get the same numbers of people. Yep, good. Okay, so in the long run, we've got 689 customers with store A, 364 customers with store B, and 365 that should be, and 1946 customers with store C. Now it doesn't quite add up to 3,000, and that can happen if you've got more than 2 states, but rounding to the nearest whole number, that works. So that's the number of customers at each store. Okay, so we can calculate that as a percentage, given that we know there were 3,000 customers. Okay, so, and you might actually, I think the rounding will be okay. So 689 into 3,000. Sorry, I should have times by 100 to make it as a percentage, but I can do that myself. So that's 22 to the nearest percent, so 23%. 365 out of 3,000. That's 12.2%, so 12%. And then 1946 out of 3,000. Sorry, Control Enter, is 65%. Check that your percentages add up to 100, but they do. Again, you might get slight rounding issues off by 1, but in this case it adds up to 100. So long-term share of customers at each store is a percentage, so 23% at store A, 12% at store B, 65% at store C are the long-term percentages. Now, you'll remember I said that the initial state doesn't matter. So actually, we could have found these values not by worrying about the initial state, just by doing the transition matrix, to a large power. And we would have found, so you can see along the whole top row, so regardless of where they shopped from previously, 23% shop at store A in the future. Regardless of where they shopped from previously, 12% shop at store B in the future, and regardless of where they shopped previously, 65% shop at store C in the future. So you actually don't need to use the initial state at all. You can just raise the transition matrix itself to a really high power. And again, you want to check that power of 51 also gives the same values, so that you know that you've actually reached the steady state. Okay. Alright, sorry, I know that's a long video, but working through a whole lot of problems involving transition matrices and Markov chains. Exercise 12C.3 is the work for today.